Hello everyone, welcome back to the latest lecture session. In the past, let's say 10 or 15 sessions, we have been looking at removing one set of compounds or the other from the water. Grit, core screens, right? And then headworks, preliminary treatment. Primary treatment, we looked at suspended solids. In secondary treatment, we oxidized most of the organic content, yes, or BOD. And what do we have after the secondary treatment, or after part of the aeration? Let's say we have still a lot of microbes, but they are relatively flock forming, or microbes that can form flocks and can settle out. So still you have water which is relatively free of soluble organics or soluble COD, but you have microbes. So you need to remove that or those microbes by settling them down. So in the case of settling, obviously our friend is gravity, and we looked at Stokes' law. We looked at sedimentation earlier when we were talking about wastewater treatment, I guess, in the context of preliminary or mostly primary treatment. So here again, same principles, so we will not go into detail. Let's see. So what do we have? We have the secondary clarifier or secondary sedimentation tank. The first sedimentation tank, we looked at removal of suspended solids. Here we are trying to remove the suspended microbes or such, which have formed flocks, right. So that's the aspect out here. So goal, I guess, let me write it in this way. So I have the relevant flocks out here, and this is my water. Right now I can't use this, but given enough time, what's going to happen? I'm going to have clarification, right. I'll have water that is relatively clarified. And this, as we saw in the video, is the supernatant decantation. We looked at that. So we are going to have clarification. One aspect is clarification. So what will this lead to? It will lead to a water that has less suspended solids. Otherwise, all my microbes will come up as suspended solids. And then all the flocks would have settled down, right. Okay, so this is what I want. But I am not just concerned about this, I also need to look at this. Part of it will be recycled, part of it will be wasted. So even the cost of recycle and treatment after wasting, this is recycle, this is sludge treatment, or let us say wasting. Let us see. What do? I need to transport it somewhere or look at anaerobic digestion and such. So if the volume is high or the mass is high, the cost will be high. So there I want to see to it that thickening of sludge happens such that most of the water within this particular flocks is removed. So two aspects: clarification of the water or supernatant above, and good thickening of the sludge, so that the water is coming out of this particular sludge. So let's see what are the relevant process involved. Let me see what else I have here. Obviously, to produce the clarified effluent and to provide higher solid concentration in return activated sludge or such. How will we provide higher solid concentration? By removing the water, right. If I have more water in the sludge, obviously the solid concentration is going to be less. So let's move on. So this is what a clarification tank looks like. So we looked at this. This is a circular one, relatively easy to build and maintain, right. That's what we already know. So you have the sludge scraper here. This is how sludge will be scraped, and this is in this kind of a shape. This is the side view. So that will collect, or the sludge will collect here, sludge hopper. And where is the water going to come from? From the center here. You can see the center, top flow, and then it will flow radially, right. And the covered launders or such here, upflow baffles. Yes, you have the baffles out here, so that you have the quiescent or laminar flow conditions. Yes, that is what you are going to have. Yes, and this is the green baffle scum. Yes, and you can walk here and for maintenance and such. Again, the MLSS is going to come from the bottom, go up, and then it is going to go out here, and during that time the flocks will settle down to the bottom. Once they settle down to the bottom, they will be scraped by the sludge scraper into this hopper. Let us see. So that is the, what do we say, working, if I may say so. And how does it look like? This is what it looks like. So, you can see in the internal, what do we say, basin, the quality of the water, and by the time I guess it goes out here, this is where your effluent will be, the treated effluent, and that is where you see it is relatively better. And depending upon the maintenance of such, you can have scum or even sometimes nocardia foaming, but foaming typically in the aeration tank, not here, let us see, but you can see this scum being removed by this scum scraper or such here. So, you see the baffles and then the treated water, this is the treated water here, right. So, let us see what else we have. What are the types of settling we will encounter? In general, if you look at it, what do we say, holistically. So, in the top zone, how is the clarification occurring, right? You have solids coming down. So, you can say it is maybe what do we say, zone settling, because we saw this in our video, right, where I just took out the MLSS, put it there and it settled within 30-40 seconds. Thickening, we did not see that there, but it is not so straightforward, right. Let us see where else or what other kinds of settling we take look at. Type 1 settling discrete, as in each particle does not influence the other or interfere the settling of the other particle, right. This occurs in the topmost layer, not much, but again topmost layer, and solid concentration, where solid concentration is relatively low, okay. And type 2 settling, this typically occurs in the inlet area, right. If it is rectangular or even if it is upflow, during that inlet area you will have the solid particles or flocks coming in contact with each other, bigger flocks being formed. So, just below the uppermost region, as solid concentration is high enough for flocks being formed. So, that is when you are going to have, here you are going to have our inlet area type 2, and where the concentration is less at the uppermost reaches, it is going to be type 1 settling, let us see, right. And below type 2 zone, solids are carried to sludge blanket, type 3 settling, right, zone settling, that is what we see. So, it is zone settling here, let us see. And one aspect here is, there is obviously going, initially there is going to be the velocity is going to be relatively constant, but as the solid concentration in this zone increases, the water will find it difficult to find space to move out, let us see, right. The water has to move out, yes. So, that will take as the concentration increases, that will be difficult. So, the velocity at which this zone comes down will decrease with increasing concentration within this zone. So, large number of particles form blanket that overtakes other particles. So, it more or less traps and takes it down. So, this is what you would see beneath that zone 2. And in the lowest region, where it's we are talking about thickening. So, these 1, 2 and primarily 3 will look at clarification, yes. And with respect to thickening, what is happening here, type 4 settling at lowest region and at sludge blanket depth. Water is displaced from the pores because the particles settle down and compress the lower regions. So, due to that weight, if I may say so, or mass, the water is squeezed out. So, that is the type 4 settling. So, compaction occurs in a way, particles compact as settling occurs. Typical sludge blanket depth is 0.3 to 0.6 meters. So, that is another aspect. You do not want to have a very thick sludge blanket, because then you are going to start having anaerobic conditions and relevant issues, let us say. So, design criteria, what is it that I am concerned about? Here it is again sedimentation. So, obviously, surface overflow rate is an issue. Q by the planned surface area. So, that is what we have, and typically we want surface overflow rate to be between 8 to 16 meter cube per meter square per day, right. Meter cube per day is the unit of Q, meter square is the unit of the surface area, let us see. And solid loading rate, why is this important? Solid loading rate obviously is when you have this and water is coming in here. So, Q is coming from here and QR is coming here. So, what will also be here? Q plus QR, and we know that the microbial concentration here is X. So, Q plus QR into X will give me an idea about the mass of the microbes coming into my sedimentation tank, and divide that by area, I get this sludge loading rate per unit area. So, I want that to be looks like 1 to 5 kg per meter square per hour. Why is that? Looks like if I increase it further, the sludge blanket depth will increase, okay. And if that increases, what is going to happen? You are going to have septic conditions and relevant decomposition there. You don't want that to happen within your secondary settling tank, right. So, that is something to keep in mind with respect to solid loading rate. So, my PhD student Bharat informed me about this, right. So, thanks to Bharat. So, design criteria, as I mentioned, depth is also what do we say, relevant because it plays considerable role. That is what people saw empirically too. And 3 meters if the surface area is greater than 28 meters square, less than this, these are typical thumb rules obviously. And here is where we see one graph, I guess, which I got from Dr. Bill Batchelor, my PhD advisor, right, whom I learned everything from, rather, not just this particular graph obviously. So, what do we have out here? Monthly average effluent suspended solids concentration. So, here I have the suspended solids concentration in the treated wastewater, and here I have the clarifier depth, but this is in feet. As you see, with even 12 feet, I think 3 feet is equal to approximately equal to 1 meter, right. So, 4 meter here as such, but for these kinds of what do we say, plants, we do not know how they are maintaining it. At relatively higher depth, around 16 or 18 depth, that is when you saw very low suspended solid concentration, right. So, you see that, okay, here we have it in meters, 3.7 meters to 5 meters. So, around 4 to 5 meters looks like was the sweet spot for most of these plants. And what was the average overflow rate? It is 678 gallons per day per square feet, let us see, right. So, that is one aspect that you can use to compare, let us see. So, what else do we have to look at? Until now we looked at suspended what do we say, systems, as in the microbes were suspended in the water, right. We have microbes that were suspended in the water, and mostly it is because we were providing air from the bottom. In the video you would have seen a fine bubble diffuser that I held in my hand, water goes in and very fine bubbles come in. So, you are going to have suspended systems, that is what we saw until now, sequential batch reactor or activated surge process or such. So, another such what do we say, type of system is the attached growth system, right. So, here it is not what do we say, suspended. For example, for an example of attached growth, so in drains or such, or places which are frequented by what do we say, water, or which frequently come in contact with water with organic content, you see green or slimy layer, right. So, that is again attached growth. You have a media or a surface onto which your microorganisms attach, and you have a biofilm developing, right. So, that is an attached growth system. Let us see where we are and move forth. So, not one for definitions, you do not need to mug this up, just to understand that process where the biomass is attached to a particular media. The media can be different forms. For example, here I have it for MBBR process, moving bed biofilm reactor. So, I just have it here. My son always messes around with this in my office. So, I am going to hold this up, right, and in different directions, relatively hollow. So, again inert media, I guess why do they prefer this? Because you have this as a combined system. So, you have microbes thriving on this, and you can also have this as a moving bed biological reactor. So, here I have these suspended in the water, and with aeration I am going to have what is it, these being suspended in water, but these will provide surface area for the microbes to grow. But if I do not, what do we say, keep them suspended and just leave them, let us say, but then we will not use this different kind of media. So, what is going to happen? We are going to call that as the attached growth system. These materials provide the surface area for the microbes to attach onto or grow on, let us say. So, that is the relevant aspect. Right. So, attached media, but MBBR it is not a typical attached growth system, it is neither here nor there, but I wanted to mention that here. Let us see what else we have. Types of attached growth. So, one is trickling filter and other is rotating biological contactor. So, as the name indicates, pardon me, it is a rotary or rotating biological contactor. So, it is self-explanatory, you have a contactor which keeps rotating, we will look at that. Another one is trickling filter, but when we think of filter, we think of, let us say, activated carbon or sand filter and such, but then the head loss will be too high, right, and you will have clogging way too often. It is not a filter per se, but it is only different kind of media that give a surface for the microbes to thrive upon. But again, let us look at these aspects and move on. So, trickling filter, wastewater trickles over the medium, and to use the organics or to degrade the organics in the presence of oxygen and the nutrients, you are going to have a biofilm developing over the medium, let us see. So, trickling filter, what is it that you have? This is a typical schematic, we will look at one later. So, from this particular, what are they calling that, F, distributor arm, you see that water will be distributed and this will keep rotating like this, right. And what else do we have? We have the filter floor, we have the under drainage, obviously water has to drain out, we have the walls, yes, we have the media, this is the media obviously on which the microbes will grow, we will look at the picture soon, and we have the distributor support influent, where is that, E, okay, distributor support influent, distributor arm, and then G is the vent. Okay, so I am unable to find G out here, and then the discharge tunnel, let us say, right. Let us look at the, okay, this is the trickling filter that you can see. You can see various trickling filters in the background, but here you can see the distributor arm and you can see the filter media. So, it is not per se a filter, but we call that a trickling filter though, right. So, here it is not, when we say filter, we talk about it in terms of physical separation of the relevant particle from the water. Let us say I have a cloth and I put in water that has a lot of sand, I am filtering it out, let us say, right. But here it is not filtration, it is actually degradation, but we still call that a trickling filter. Let us look at the close up. So, here you have the filtered media, and after what do we say, the biofilm has developed due to what do we say, the organic content available there and the oxygen content. This is what we have, filtered media with a biofilm, let us see. So, let us just look at how the biofilm grows or such. So, I have this media or the surface, this is my media, and on this over time the biofilm will develop, let us see, right. This is my biofilm, and MIT Open Courseware tells me that it can be anywhere between 10 micrometer to even a few mm, let us see, or 10 mm, let us see, right. So, you can see that there can be a wide what do we say, variation, but what else will you have? You will have a stagnant liquid layer here, stagnant liquid layer here, liquid, and so through this what needs to go in or what needs to diffuse through. So, this is where the degradation takes place within the relevant biofilm, but what has to be degraded? Your organic matter has to degrade, and it needs your nutrients and it needs oxygen, right. So, that is what you have, these need to diffuse through this particular stagnant liquid film here, and here you will have the bulk liquid, the water that is flowing or trickling over this particular layer, let us say, this is your bulk liquid, and here you have your oxygen or the air. So, that is what you have out here, right. So, that is how the biofilm looks from the side view, if I may say so. So, let us look at other data here, characteristic substrate concentration profiles within a biofilm. So, I guess we are sweeping this or swapping that picture from left to right here. So, here is the attaching surface or the media. So, this is the biofilm, this is the stagnant layer or the diffusion layer, this is the bulk liquid. So, obviously, in the bulk, the surface, not surface, the concentration of the relevant organic matter, right, or the substrate is going to be high. So, through the diffusion, why will it go through the diffusion layer, or why will it diffuse? As we know, only if there is a concentration gradient. If the gradient is concentration or such, anyway, varying, so that is the relevant aspect. So, we have shallow and we have deep. Let us just look at the shallow, let us see. Okay, so, we have this, it is diffusion due to concentration gradient, and then you have the substrate penetrating further, again fully penetrated, and with that case you are going to have degradation of the organic content within the biofilm, right. The organic content in the biofilm will be degrading it. So, that is why the concentration here will be less than what it is in the bulk liquid or bulk layer, let us see. So, this is how you see, and deep I guess you have other cases. So, let us move on. So, biofilm profile and slowing, let us see, you have two aspects that can lead to what do we say loss of this biofilm. Obviously, you will have decay, that is something we always know, but in general you will have erosion, right. In general you will always have this constant loss of biofilm mass, let us see, right. So, that is what we have. Slowing though, biofilm grows over time, then sometimes you see sections itself falling down. So, that is called slowing, let us see. So, just a picture. So, if this is the media and this is my biofilm, let us say, erosion is, let us say, sometimes looks like small particles and such, due to various reasons will be eroded, let us see. But sometimes whole sections, let us see, will fall off. This is slowing, right. So, this can happen, and again you need to obviously look at the loading rate and such. So, recycling of the effluent, why do we need it? Because it improves the oxygen transfer and more importantly the hydraulic distribution, let us see. You have to recycle this effluent, and typically you would do it before the settling, let us see. And here we have different types of trickling filter, low rate, intermediate and high rate. As you can see, the loading rate varies 0.08, 0.24 and 0.4. And removal efficiency also is slightly depend upon your rate of loading. Relatively low loading rate, the highest efficiency. Why is that? Because now I am distributing the water at a very slow pace. So, the rate at which the water is going through the filter is less, meaning the the organic content has more time, or it can diffuse into the stagnant layer and the biofilm, and the microbes thus can have greater access, if I may say so, to the organic content. But if I am sending the water through fast, not enough time for diffusion into the relevant biofilm, so relatively less efficiency out here, let us see. So, that is one aspect to understand. Why is it advantageous? Here I am not pumping in air, right, I am just using air that is present in the atmosphere, and thus less energy requirement, pretty simple operation, and depending on how I can recycle, it can withstand shock and toxic loads. And looks like it depending upon how I maintain it and recycle, the sludge thickening is better. But again, every time it comes down to money, and so as you see the operation is pretty simple, let us say, right. So, what are the disadvantages? Obviously, again depending upon how tightly or not how tightly within a unit volume, how much biomass I have, that will allow for or tell me how efficient the process of degradation of organics will be. So, due to that, as in I am assuming relatively less biomass or microorganisms per unit volume, you are going to have relatively poorer effluent quality. Obviously, odor will be an issue. Sometimes you can have inorganic removal, especially within, not inorganic, anaerobic removal, especially within the relevant biofilm. So, odor can be an issue, and obviously fly nuisance. Lesser nitrogen removal depending on the thickness of the biofilm, and obviously because it is exposed, it is pretty sensitive to low temperature. So, these are the aspects, but primary aspect is odor and poor effluent quality. So, rotary biological contactor. So, it consists, as is obvious from the name, rotating discs over which biofilm gets attached. Thus, it is called attached growth system. Discs rotate or move through the wastewater for aeration and mixing. So, you have water here and the disc here, and this rotates, right. So, when it is underneath, the biofilm comes in contact with it, and also when it is overneath, you have bringing in air, right, you are circulating air. So, slime layer forms over the disc surface, aeration is controlled by the rate of rotation of the discs, and no recycling is required, but obviously effluent quality will be less. So, here you see the rotating biological contactors, RBC with the wastewater flow, typically it will be in this direction, right. These are the discs, and you can see the slime layer that has grown or the attached biofilm all over, let us say. Some cases relatively less, and some places relatively more, right. So, MBBR, that is something I already discussed, and now we will move on to another aspect, but let me finish this up. So, biological process loading rate, let us just compare the three different cases. One is the activated sludge, which is the suspended process, and two, attached growth, which are trickling filter and rotary biological contactors, right. Obviously, as you see, organic loading rate is relatively much higher in the case of the suspended process when compared to the trickling filter, and more specifically with respect to the RBC. But simpler operation and relatively less flow rates coming in, then you can go for trickling filter, but space is an issue or area has to be available. If not, obviously you will have to go with activated sludge process. As I mentioned, and that is why I had the reminder with respect to MBBR. So, you can have both suspended and attached. Some people have looked at providing media, right, and the media can be these kinds of MBBR moving bed biofilm reactor, right. So, you can have both attached. So, this will be pumped in, this is air coming in, and this is my media upon which the microbes will grow, let us see, right. So, that is MBBR system. So, next what do we have? Disinfection. Until now I have removed, what do we say, organic content, suspended solids, grit, different, what do we say, plastics or such that might come through with the core screens, and I removed the microorganisms in the secondary clarifier. What else am I left with? Most of the pathogens or enteric, what do we say, organisms that come in with the influent wastewater are killed during the activated sludge process or this biological process. Why is that? They can't withstand this thriving microbial community. But still you will have some, what do we say, pathogenic organisms, and typically you do not want to release that into the environment or the water. Thus, you want to disinfect it, and we will look at this in the next session. But disinfection, there are different ways. Let us see how they do it in India and what are the better ways. But with that, I will end today's session, and thank you.